Let's go for the action movie setup on this one. You've got a gas tank on the car. You've strapped the plastic explosive to that gas tank. In seconds, the thing's going to explode. When it explodes, there's going to be a sudden burst of flame, lots of gases shooting out of that, and probably some solid residues left behind. What did we just do? We did a bunch of chemical reactions. And each of those different substances started and ended in different states of matter. As a result, it's going to be really important for us to specify the state of matter for each reactant and product that we have in our balanced chemical reaction. Now, we're going to use these 4 symbols to handle pretty much all those cases. There are some additional ones, but we won't focus on them in Chem 1. They're much more specialized. Solids are pretty self-evident, and so are gases. Those are pretty obvious to us. Now, liquid, we write a very specific way. We use a cursive L. Why? Because if I just write it as a lowercase l like that, it looks like I've got 1 in parentheses. And that can be really confusing, especially if we're writing down a substance and it looks like that's implying something about a transition metal's charge, or that we're multiplying it for some other sort of a calculation. So we use a cursive L to make sure that it's easy to spot. Now this one tricks people a little bit at the beginning, but it turns pretty intuitive really quickly. Aqueous, AQ, means that it's dissolved in water. And it means dissolved. It doesn't mean just suspended in. What's the difference? I'm glad you asked. So if I take some vinegar that's an aqueous solution, where we have acetic acid, other flavor compounds, and other things that are uniformly dissolved in water. If I'm talking about oil and vinegar, when you shake that, the oil and the vinegar do not mix. The oil would not be aqueous. You'd have liquid phase oil, and we'd have to be more specific about the molecule than just saying oil, but we'll leave that for later. And then we'd have our aqueous solutions of acetic acid and all those other flavors. Big distinction, it's got to be dissolved in water. If it's not dissolved in water, it's going to be a liquid still. And we're also going to have some cases where there's going to be a bit of nuance there. Now, one thing I really want to highlight on this one. You've seen some of those cases where you mix 2 solutions together, and all of a sudden you get this really fine powder that's suspended in it. Those things are not dissolved. They are tiny solid particles. If you let it sit for a little while and the solids can settle out, or you can use a filter to collect all the solids that are in it, that is not going to be aqueous. Those are just going to be tiny particles of solids suspended in water. They actually have to be dissolved, and that means down to the single molecule level. Now with that bit of a nuance, I want us to refer to one of the previous videos. When we handled this reaction, combining hydrogen and oxygen to generate water, we also should have shown our states of matter. Now, we don't always know what those states of matter will be, because we don't always know what the molecule should look like. We can draw a Lewis structure for it. We can picture it in 3 dimensions. We can even from that start to infer whether it'll be really sticky to its neighbor and probably be a solid or probably be a gas. So we're not always going to make you come up with it on your own. But there's times where it should be really obvious. And this is one of those cases. Now, you know the states of matter for hydrogen and oxygen, typically. And I'll also point out that if you started out with both of those, like in the case of the Hindenburg when it exploded, did it start raining immediately, or did you have steam? So go ahead, pause the video for a moment, and write down what your states of matter should be in your balanced chemical equation for hydrogen reacting with oxygen. Okay, and clearly in this video we like explosions. So we're going to have H2 and O2. We know that we're going to need 2 of these H2s, 1 O2, and when we put them together and combust them, we're going to get H2O. We'll get 2 of the waters, 4 hydrogens on this side, 4 on this side, 2 oxygens on this side, 1 times 2 oxygens on this side as well. So we have a balanced chemical equation. We specified that the hydrogen is going to be a gas. After all, we said, what about the Hindenburg? And it was floating, and the dirigible was filled with hydrogen gas. Oxygen is obviously a gas as well. Otherwise, your breathing is about to become very labored. Now, water we're used to thinking of as being a liquid, but it did not immediately rain, or you're going to have a big cloud of steam like I just rhetorically asked, which means that it's going to be gas phase water. So you can see here that all three of our states of matter for this would be gas. Now, from this point forward, if we ask you to think about a reaction, always make sure that you think about what the reactants and products are going to be, and you think about what your states of matter probably will be. Later on, when we add some of those intermolecular properties in, we'll start being able to infer whether it's a solid, a liquid, or a gas. But for the time being, you'll definitely need to be able to recognize it when it's really obvious, like oxygen, and really obvious like calcium metal, or steel, or dissolved iron 3 ion. See, all of these cases you should be able to identify that the iron 3 ion would be aqueous. Iron metal would be solid. You should be able to infer those things, but we won't ask you more complicated cases.